Hello friends, in this video we are going to study about the architecture of the first math coprocessor 8087. We will study its architecture, or we can say its block diagram, and we will see the function of each of the blocks present in the diagram. Okay, so let us start with our topic. The 8087 math coprocessor is the first coprocessor developed by Intel to pair with the 8086 and 8088 microprocessors. The work of the coprocessor is to provide easy and fast calculations to the microprocessors, because these complex arithmetic and trigonometric and logarithmic calculations, they cannot be performed by the microprocessors. So to do such types of calculations, the coprocessors are developed. So 8087 was the first coprocessor. So here in this video, we are going to study the architecture or the block diagram of the 8087 math coprocessor. The architecture or the block diagram is divided into two parts. One is the control unit and other is the numeric extension unit. So the block diagram is divided in two groups, control unit and numeric extension unit. Now control unit, it controls all the communication between the microprocessor and the coprocessor. Microprocessor will be 8086 or 8088, and all the communication between the microprocessor and coprocessor, that will be handled by the control unit. And the numeric extension unit, it handles all the numeric calculations done by the coprocessor. Okay. So if we talk about the functions of control unit and numeric extension unit, control unit handles all the communication between the processor and the microprocessor. So control unit is handling all the communication between the processor and the memory of the microprocessor. Operations like it can receive and decode the instructions. Okay, it is going to receive the instruction, then decode them and execute them. Read and write the memory operands and maintain parallel queue, etc. All these functions are performed by the control unit. So control unit is handling, or we can say it is controlling the communication between the microprocessor and the processor. Then we are having the numeric extension unit. So this unit, it handles all the numeric operations, okay, like numeric calculations, all the type of arithmetic and logical, data transfer, translation, all type of the operations which are performed by the processor, okay, calculations, numeric calculations which are involving the data, they are being done by the numeric extension unit. So all type of instructions, they are being processed or handled by the numeric extension unit. So this, we see here that block diagram is divided into two parts, control unit and numeric extension unit, and what is the function of these two parts. Okay. Now let's see the different components of the control unit and the numeric extension unit. First we will see the block diagram. This is the block diagram of the 8087. You can see that this complete block diagram is divided into two parts, the control unit and the numeric extension numeric execution unit. Okay. Now in the control unit, you can see we are having control word, status word, data buffer, addressing and bus tracking, exception pointers. To this we are attached the data lines, the status lines and the address lines. Okay. Now this data buffer is providing the NBU instruction. Okay. Here we are having the operands queue. Then here we are having the tag word. Now in the numeric execution unit, we are having the exponent bus, the fraction bus, exponent module, microcode control unit. Then here we are having the stack, okay, programmable shifter, arithmetic module, temporary registers. So all these different parts of this numeric execution unit, they are performing the numeric calculations, okay, numeric processes like arithmetic, logical and data transfer instruction, all them are handled by this. Whereas control unit, it is just communicating with the microprocessor because it has the access of the data bus, status bus and the address bus. So through this, it can communicate with the microprocessor. So this is the complete architecture, or we can say the block diagram. Let's see different, let us first study these two groups in detail. First we will start with the control unit. So as I have said that it is the communication between the processor and the microprocessor 8086. So we can say that it is acting as an interfacing part. Okay, interface is the communication link. So we can say that it interfaces coprocessor to the microprocessor. Also, it synchronizes all the operations of the coprocessor and the microprocessor. Now this control unit, it consists of different parts. One is the control word. Then we are having the status word. Data buffer. Okay, these are the three main parts of the control unit. Now we know that the 8087 coprocessor, it also has its own instruction set. and in that instruction set, every instruction is having the prefix F, okay, and escape ESC is added before every instruction. So just like the 8086 microprocessor is having the instruction queue, 8087 is also having its own instruction queue where it is fetching the instructions. Okay. Now, when it is fetching the instruction, if it encounters the prefix escape or F prefix is added up against every instruction, then that instruction will be decoded by the coprocessor. Otherwise, it will be ignored by the coprocessor. So, any instruction So any instruction which is having an escape prefix, that will be decoded by the 8087, otherwise it will be ignored. And just like the 8086, all the instruction, they will form an instruction queue, and from that instruction queue, the instructions will be one by one fetched and decoded. As I said that the control unit is having three main parts: control word, status word, and the data buffer. So we will study these registers. First we will start with the status register is a 16-bit register. Okay, 16 bits are there, and each bit is having some specific function. This status register, it tells the overall status of the 8087 coprocessor, that in what state that coprocessor is. So overall condition will be told by the status register. Now in this status register, status word is written. The contents of the status registers are called the status word. Now, if you want to access this status register, then there is a special instruction called the FSTSW. This instruction is used to access the status register. This is store the status word. So when we write this instruction FSTSW, there will be, after that instruction, there will be an address. Okay, that address will be stored in a register. Okay, so at that address, the status word will be copied. Okay, so status word will be stored at that specific location. And when these contents are stored at in the memory, then by accessing that memory location, we can get that what is the condition or the what is the overall status of the 8087 by examining the bits of the status register. Okay, now let's see that how the 16 bits of this status register they are specified. So these are the 16 bits of the status register. You can see starting from 0 to 15, these are the 16 bits. Bit number 15 is the busy bit. Then bit number 14 is the 14, 10, 9 and 8. These are the 4 condition code bits from C3 to C0. Okay. Then 13 is empty, 11 is empty, 6 is also empty. Then this bit number 12 is the ST, that is top of stack. Then we are having ES, which is the error summary. Then PE for precision error, UE is for underflow error, OE is for overflow error, then ZE is for zero error, DE is for denormalized error, and IE is the invalid error. So this is how the 16 bits they are specified of the status register. So let's study the function of each of these bits. When this bit is 1, means it is set. It means that it indicates that the coprocessor 8087 is busy in executing some task. Okay. So when this bit is set, means its value is 1, it indicates that coprocessor is busy. After that, we were having the condition codes bit. From C0 to C3. These condition code bits, they indicate about the various conditions of the coprocessor. Then we were having the top of stack bit. Stack is a memory location, means a group of memory locations is there. Okay. And in the 8087, here also we are having the stack. So top of stack, it indicates the register which is the beginning of the stack. Means top of stack, it holds the address of that which register is the starting register or the beginning of the stack, from where the stack is beginning. There we were having 8 registers in the stack. So out of 8 register, which register is the starting register? So it indicates a register as the top of stack out of the 8 registers. Then we are having the exception flag, or we can say error summary. This bit is set to 1 if any of the exception flag present in the status word they are set. You can see in this, here we are having precision error, underflow, overflow, zero, denormalized and the invalid. So out of these errors, if any of the error is set, okay, then this bit is also set to 1. So if any of the exception flag bit is set, then this bit is also set to 1. Now in the exception flags, we were having the first flag as the precision error, This error is generated whenever the result is exceeding the selected precision. Okay, so this bit will be set to 1 whenever this error occurs. After precision error, we are having underflow error. Underflow. If this bit is set to 1, it means that the result is very small to be uh, adjusted in the register. Okay, so result is too small to fit in the register. And if the result is very large to fit in the register, then we are having the overflow error. Okay, so whenever these errors are occurring, the corresponding bit is set to 1. After overflow, we are having the 0, divide, exception flag. It means when this bit is 1, it means that we are trying to divide a non-zero number, non-zero value by 0. So we are trying to divide a non-zero number by 0. So whenever this type of error occurs, this bit will be set to 1. After that, we are having denormalized. Denormalized error occur whenever any one of the operand is denormalized. Okay. Then we are having invalid error or invalid operation. Invalid error occur whenever there is any invalid operation occurring. Like if we want to push a number which is exceeding 8-bit value into the register. If we want to pop an empty stack, means a stack is empty and we want to get a number from it. Okay, so all these are invalid operations. So whenever any invalid operation is occurring, this error will be occurring and the bit will be set to 1. Like if we want to take a square root of a negative number, that is an invalid operation. If we want to push a number which is exceeding the limit of the register, it means the register is of 8-bit and we want to store a 16-bit number into it. So that is also an invalid operation. Like I have said, popping contents from a empty stack, that is also an invalid operation. So in all these cases, invalid error will occur. So this is the status register. We have studied all the bits, that what is the function of these bit and when these bits will be set to 1. So this was the status register or the status word. Now comes the control register. Control register is also the 16-bit register and it controls the operating modes of the 8087, that in which mode the 8087 is working. So not only the operating modes, but it also performs the rounding control and the precision control. The bits of the control register, it is having 16-bit register. It contents will be known as the control word. So the control word will be written into the memory so that in whatever mode we want that 8087 should function, we can control that mode through it. Okay. Rounding control and precision control is also done. Also, it is used to mask and unmask the interrupts. So it is also used to do masking and unmasking of the exception flags. And these exception bits which were present in the status register, we have seen that in the status register we were having the exception flags. These are called the exception errors and exception flags also. Okay, so to mask and unmask these bits, their masking and unmasking is done in the control register. So for these exception flags we are having corresponding bits in the control register or control word also. Now, just like in the status register, status word, if we want to access the status register, we were having the special instruction FSTSW, that is to store the status word. Now, if we want to write the control word, okay, because status register is always read and control register is always written. Okay, so to write the control word, then we have the special instruction FLDCW. That is, LD is for loading, C control word. Okay, so this instruction loads the value into the control word. So whenever we want to write the control word, we will use the instruction FLDCW. F is always used for the 8087 coprocessor. LD is for loading and CW is for the control word. Okay. So this is the control register showing the 16 bits. Okay, how these 16 bits are defined, you can see 15, 14 and 13 bit, they are not in use, they are reserved for future purpose. Also bit number 6 is not in use. Then we are having IC, which is for infinity control. 10th and 11th bit, they are for the rounding control. 8th and 9th bit, they are for the precision control. So all type of controlling is provided by here. The control word, infinity, rounding, and the precision control. Then M, this is for masking and unmasking the interrupts. Interrupts means these are the exception flags. Exception flags, they work as an interrupt. Okay. So here we are having precision, underflow, overflow, zero, denormalized, and invalid. Just like in the status word we were having these exception flags, here also we are having the exception flags. If we want to mask them, then bit will be 1. If we want to unmask them, then bit will be 0. So 1 means mask and 0 means unmask. And the bit which is like, suppose OM means third number bit is 1, and here mask bit is 1. So overflow exception flag will be masked. Okay. Now in the infinity control we were having 0 and 1. So it provides the type of projectivity or assignment to the numbers given. If it is 0, then the number will be single and unsigned, and if it is 1, then it will be treated as either positive or negative. Affinity will be provided. Then rounding control means that when we are having a number, then to what nearest digit that will be rounded off. Okay, if it is 0 means round the number to the nearest number or the even number. Then 1 means round to the down number, round to the up number. Then 1 means truncate. Then precision control, for precision control we are having, if it is 00 means 24 bits, 01 is reserved, 10 53 bits, and 11 is for 64 bits. Okay, so these are the 16 bits of the control register, how they are defined and their functions. So we can see that the control register, it is providing the rounding control, the precision control, and the exception mask. Okay, so these three things are provided by the control word. Rounding control means it determines that the type of rounding to be done to the result. Precision control means that how much precision is present there in the result. Then exception mask, it is used to mask the exception flags. If the corresponding bit is set to 1, so error is masked means error is not going to occur, and error is not masked means error is going to occur. So when it is 1 means masking is done, and when it is 0 means unmasking is there. So these operations are performed by the control register. Now let's coming back to the control unit. Okay, in the control unit we saw the control word, the status word. Now comes the data buffer and the addressing and bus tracking exception pointers are there. So in here we are having two pointers also, instruction pointer and data pointer. Instruction pointer points towards the instruction which is currently executed. So instruction pointer, it mainly contains the address of the escape instruction. It is a 32-bit complete instruction pointer. This instruction pointer is of 32-bit. Out of these 32 bits, it is divided into 20 bits and 11 bits. The 20 bits address is of the escape instruction. and these 11 bits are from the 16 bits of the instruction. In that 16 bits of instruction code, we are having 11 bits and 5 bits. 5 bits are always 11011 for the ESC, and remaining we are having the 11 bits. So those 11 bits are used here. Okay, and 1 bit is always 0. So 20 plus 11 plus this 1 bit makes it 32-bit instruction pointer. So out of this 32-bit, 20 bits are the address of the ESC instruction, 11 bits are coming from the 16 bits of the instruction code, and 1 bit is always 0. So this is the instruction pointer. Another pointer is the data pointer. Just like instruction pointer is carrying the address of the instruction, data pointer is carrying the address of the data. It is also of 32-bit. Out of this 32-bit, 20 bits are the memory address of data, means the actual data address, and the remaining 2 bits, they are, sorry, remaining 12 bits, they are always 0. Okay, so just like this, we are having 2 pointers, instruction pointer and data pointer, which are of 32 bits, and how these 32 bits are defined we have studied here. So again, if we see the block diagram, it completes the control unit. Okay, now comes the numeric execution unit, which is performing the numeric calculations. For performing this numeric calculation, it is having different components here. The main component is this register, stack and the tag word. Okay, so we will study these two. In this register stack, you can see that it is having 8 registers here. Each of this register is of 80 bits. Okay, means 80 bit of data can be stored in each register. Now the top of the stack, that will be indicated by the status register. In status register, we have studied 1 bit is for the top of stack. So from there we will see that which of these 8 register is the top of the stack. So if we see the numeric execution unit, its main part is the register stack. Now this 8087 coprocessor, it internally works with 8 bit of data. Okay, and to store this 80 bit of data, it is having the stack, which consists of 80 bits registers. Means there are 8 registers and each register can store 80 bits, and these 8 registers are labeled from 0 to 7. Okay, like for the 0 register we are having the address 000, then 001 till we are having 111 for the 7th register. This is for 0, this is for 7, that is the last register. Now in this stack, they use the last in first out, that is LIFO format. That is the content which is last input or stored into the stack, that data will be the first to come out of the stack. So last in, first out concept is used here. Now every time we want to use this stack, we have to initialize the stack, which is done by the top of stack bit. Okay, and this top of stack bit, it holds the number of the register, which is the TOS, that is top of stack. Suppose that this is at 0, it means that this 0 register is the top of the stack. From here the data will be stored. Okay, now data is stored and retrieved from the stack, just like we do in the 8086 microprocessor. We use the push and the pop instruction. So here also these instructions are used to store the data and to retrieve the data. Okay. Now other than this register stack, we are having the tag word. This tag word is stored in the tag register. Just like control word and status word, they are stored in the control and the status register, tag word is stored in the tag register. And this register gives us the information about the contents of the stack register. There are 2 bits for each register in it. Okay, so it is of there are 16 tag bits. This is also a 16-bit register. So if we see its format, so for every register we are having 2 bits. So for this we are having 15 and 14. Then we are having 13, 12, 11, 10, 9, 8. So for every register we are having 2 bits here, and the tag values will be 0 0 if the tag value is, means it is valid. 0 1 means it is 0. Then 1 0 means invalid, and 1 1 means empty. So for every register, means 8 registers are there. For every register there are 2 bits, so it is a total 16-bit register. And tag values are like this. If the tag is 0 0, then valid. 0 1, then 0 1 0 means invalid, and 1 1 for empty. Now when this 8087 it is initialized, the tag word is F F F F H. Why? Because all the registers in the stack, they are empty. So when this 8087 is initialized, the tag word is FFFF. Why? Because FFF means all the tag values are 1 1. And when the tag values are 1 1, it means that the registers are empty. So when 8087 is initialized, all its 8 registers are empty. So that is why the tag word is FFFF. So it can be asked that when 8087 is initialized, what is the tag word? Okay. So this was the numeric execution unit, in which the 2 main parts are the register stack and the tag word. Okay. So the complete architecture of block diagram, we have seen that it is divided into two parts, control unit and numeric execution unit. We have studied the main parts also, control word, status word, and data pointer, instruction pointer, register, tag and tag word in this. So that completes the block diagram or architecture of the first math coprocessor 8087. So I hope that this topic is now clear to you. Thank you.